Okay. So we were almost to the end of my second introduction, sort of the basic primer on heavy ion collision physics that is not yet the observables that ADS-CFT will have something directly to say about, but to give you context. So I had gotten as far as showing you that one can argue that at a time of 1 Fermi, the energy density was bigger than 5 GeV per cubic Fermi. And we can then compare that to what lattice QCD says is the energy density at the crossover, which is around 1 GeV per cubic Fermi. So if the stuff here can be described as on the phase diagram in local thermal equilibrium, then lattice QCD tells us that this stuff is Quark-Gluon plasma. And so now the main goal for today is to talk about the evidence for early equilibration and 8 over S and small 8 over S and such things. But before we get to that, to finish this diagram, so there's this hydrodynamic epoch after tau naught going up to some late time, during which these orange lines indicate the flow of some fluid. But then hydrodynamics ends, it stops being valid at some point, which is called freeze out, using the same word that's used in cosmology. You know, by the time the experimentalists see pions in their detector, which have traveled 5 meters, those pions 5 meters away from the vertex are not described by hydrodynamics. They're described by pions following trajectories. And so there's a process here called freeze out, which has its own issues. There's a whole set of issues in trying to describe that physics. I won't talk about them, but just to warn you that you have to transition from hydrodynamics to hadrons. These hadrons are then seen in the detector, so these green lines might be pions flying off with some longitudinal momentum. The transverse momentum is not shown in this diagram. And the first question you can ask if you want to look for a thermal equilibration, we'd like to argue for equilibration back here, but let's first ask whether there's evidence that what you have here is in equilibrium, which is easier. So is the final state an equilibrated hadron gas? Well, so what might you expect? The first thing you would expect is that momentum spectra should have a Boltzmann distribution. Thermal equilibrium, Boltzmann distribution. Now, one caveat, we don't want to look at the longitudinal momenta, because this fluid here, even if it's not precisely boost invariant, it's somewhat close to boost invariance. And in particular, the fluid over here is flowing this way. The fluid over there is flowing that way. So most of if you detect the longitudinal momentum of these pions, it does not correspond to the thermal. That's not the momentum that should be thermally distributed, because that mostly corresponds to this longitudinal flow. So the question that you should ask is, are the transverse momentum spectra thermal? And by thermal here, I mean Boltzmann distributed. So that you would expect in thermal equilibrium, you might think, this is not quite right, as I'm going to explain. I'm going to put quotes around this T for reasons that will become clear in a minute. This is not yet the real T. So the answer is yes for PT less than about 3 GeV. So if I give you a cartoon of, so I gave you a cartoon of data on how many pions there were, and now I'm going to give you a cartoon of data on their transverse momentum. So this will be the log of d squared n dpt d eta at eta equals 0. So we'll work at central rapidity, look at the transverse momentum, and on a log scale, so here's 0, here's 3 GeV, here's 6 GeV, here's 9 GeV, here's 12. On a log scale, an exponential is a straight line, and indeed you see, so there's data with error bars, which again I'm going to give you a cartoon of. You see a straight line here out to around 3 GeV, but then it stops being straight. It has some curvature like this. to give you a sense of scale, from here to here is 9 to 10 orders of magnitude. So 12 GeV pions are about 1 billion times rarer than 0 GeV pions. Okay. But the experimentalists collect data sets with much more than 1 billion events, so they can plot these spectra out to here. And so there's a change in physics in the spectra somewhere at around 3 GeV. It's not a sharp change, but there's some change here. These are the soft hadrons. These are the hard ones. Here we have an exponential spectrum. Here we have a power law. And exponential, i.e. thermal. Now, where does this power law distribution come from? This is what you expect from perturbative QCD for hard scattering. So if you calculate quark goes to 2 pions, something like that. And if you work in a regime where perturbation theory is valid out at high transverse momentum, you always get power laws, not exponentials. And so what this is saying is that these hadrons here are not thermalized. So not everything is thermalized in a heavy ion collision. When you go out to these rare 1 in a million, 1 in a billion high momentum hadrons, they're not thermalized. But most of the hadrons are in here, in PT. And they do have exponential spectra. So sounds good. But then, yes, Tom.
This is a question from 1970. I recall that in PP collision.
Yeah, I'm going to say that in a second. I know the question. It's a standard question. Let me postpone it until for a few pages of yellow notes, a few yellow pages of notes, because there's a bigger issue before you get to that one. The bigger issue is that when you do this for pions, you do it for protons, and you do it for kaons, you find that the temperatures that you extract from these slopes are not the same. So the T in quotes is the temperature you extract just from the slope of this line. And the temperature for protons is bigger than the temperature for kaons, bigger than the temperature for kaons. So this can't be the real temperature. And in fact, what you find is if I plot against mass of the hadron, so here are pions, here are kaons, here are protons, and I'm going to plot this T, which is an experimentally measured quantity, you get something which looks like this. Boom, boom, boom. And I claim that it's reasonable to think that this is the real temperature. And this slope here tells us the radial velocity. In other words, what you're looking at in this final state is not a hadron gas sitting there at rest. It's a hadron gas that's exploding outwards in the transverse directions. So let's say the beam was going this way, you do a collision, and yet in the final state you have this large radial velocity. And it's a true fact that if you take a Boltzmann distribution and boost it, it's still a Boltzmann distribution, but with a higher temperature. So this fake temperature, T in quotes, is the combination of the real temperature and the boost due to the radial expansion. And the reason that you get a higher fake temperature for kaons and protons is simple. The boost means pi k and p should have the same velocity, but protons are heavier, so they have more momentum. So the boost affects the momenta of the protons more than the momenta of the pions because it's the same boost velocity. And the fact that this is a straight line confirms that picture. And what you get out of this is that the radial velocity is around 0.6 times the speed of light. So by the time of decoupling, by the time of freeze-out, what you have is not a hadron gas at rest, but a hadron gas that is the final state of an explosion, the little bang, which has exploded in the transverse direction to such an extent that you have pions flying out freezing out from a fluid where the fluid had a collective velocity of order 0.6 c. Yes. Sorry, there are two questions asked simultaneously. You first.
Just why is not so low? Why is not 0.99?
Oh, that's because this is not the velocity of a pion. This is the velocity of the fluid. Okay? This is the collective, and there's not time. It's actually, if you go back and look in lower energy collisions at older accelerators with less energy than RHIC, this was 0.3, 0.4. So this is actually quite large relative to previous expectations. It's because it doesn't stay. At some point you stop getting this push. You stop getting a push from a. Freeze out is when you stop. You're no longer allowed to describe this thing as a fluid. And so from that point on, everybody, the experimentalists measure momenta, which remember the momentum distribution at that time of freeze out. If that time of freeze out were later, if there was more time for the pressure to act, this would go up further. There was a question there.
Yeah, so is the statement that this capital T is the temperature measured for the ions, or is it closest to the effective temperature?
So there are going to be several temperatures in this talk. This one, this T here, the one with no quotes around it, is called the kinetic freeze-out temperature. And it turns out to be around 90 MeV at RHIC. That's the temperature. So at 90 MeV temperature, we know from lattice QCD you don't have a Quark-Gluon plasma. This is a temperature of the gas of hadrons at the time when the hadrons stop bumping into each other. Okay, so after the Quark-Gluon plasma epoch, you have a gas of hadrons. You have a fluid of hadrons, let's say. Those hadrons are hadrons, but they're still colliding with each other, exchanging momentum, keeping their momentum in equilibrium as the system cools. Then the system freezes out, and you're left with a 90 MeV freeze-out temperature. Wait just a second. So I want to answer. I want to answer Tom's question now, which I didn't let him finish asking. If you do this experiment, this measurement in PP collisions, you find the same effective temperature for pions, protons, and kaons, and that tells you that that effective temperature has nothing to do with. Well, it is thought that effective temperature just has to do with random filling of phase space. If you throw hadrons randomly in phase space, that probability distribution will be governed by some temperature. And that temperature has nothing to do with the existence of some fluid. So the argument that what we are seeing in heavy ion collisions at this very late time, this is much later than we're interested in, at this very late time, is a fluid, comes from, in fact, this slope, which indicates that there's a collective velocity of the system with the pions, kaons, and protons moving outwards with a common as part of the same fluid. Now there's a question on this side.
Well, you sort of answered it. This temperature is pretty low.
Yes. Yeah, so this is not the temperature we're interested in. But, you want to, it's the first temperature you can measure, experimentally speaking. Now, yes?
So, I'm just curious. So, actually, you also find this in cosmology, but for different reasons, which is that it things just freeze out at different times, depending on their So, how can you tell that that's not what's going on here? That somehow
They all have. We know from theory that they all have strong interaction cross sections.
yeah, and the masses don't. The fact that they're heavier doesn't matter.
No, this is just elastic scattering, so it's not going to matter. But yeah, that's a good question. Okay, so I was going to use the cosmology example now, which is to say that the cosmological analog of what I'm talking about is, say, the decoupling of electrons and photons at the time when the microwave background radiation is freed from the plasma. And from then until now, those photons in the CMB free stream. Okay? Yes, there's cosmological expansion, so they get redshifted. We don't have that here, but it's the same idea. Now you can ask, if you go back in cosmology, go back to earlier epochs, what's the next much earlier epoch when you really know something? And the answer is nucleosynthesis. So is there an analog of nucleosynthesis here in heavy ion collisions? And there is. The next thing you can ask is to look at ratios of numbers of hadrons. So this is the analog of looking at the hydrogen to deuterium to helium to lithium ratios in cosmology. And in a particular paper that we looked up, many people have done this, many experimentalists have done this. They measured, this is an experimental paper from, I think it was Starr, they measured 18 ratios. I won't list all 18, but you can get more of them. The error bars just go up. But to give you some idea, you measure the ratio of number of pi minuses over pi pluses, k minus over k plus, p bar over p, lambda bar over lambda, pi over p. I'll skip ahead to some omega bar over omega, k plus over pi plus. I'm skipping ahead, ... Let me just give you a sense of how far they go. They look at k0 stars, which you have to look up in the particle data book, over k minuses. They look up, they do delta plus plus over protons. They do lambda stars over lambdas. There's 18 ratios. Okay, so there's lots of hadrons in the particle data book. Remember that these final states are complicated to analyze experimentally. There's 5,000 charged particles in the final state. So the fact that they can reconstruct the multiplicities of this many hadrons is a sign of their skill as experimental physicists. So you get 18 or more ratios, and you fit them with two parameters. And those two parameters are a temperature and a chemical potential. And so, for example, in this kind of a ratio, the two particles in the ratio have different masses. So their Boltzmann weights will be different because of their different masses. They also, this one has baryon number, this one doesn't, so mu will affect them differently. It'll affect this one, not that one. So anyway, it's a greatly over-constrained problem because there's 18 measurements and two parameters. And the first statement is that within error bars, you get, some of the error bars are bigger than others, but within error bars, you get all of them. I think the biggest deviation is less than 2 sigma. So this fit works. And so then you can pull out a temperature and a baryon chemical potential. And the temperature, this temperature is called the temperature of chemical freeze-out. The word chemical here is used to mean chemistry is things that change species. So here it's things that change one hadron to another. And the chemical freeze-out temperature turns out to be something like, the experimental error bar quoted as a range is 155 MeV to 180 MeV. Sometimes this is written as 160 plus or minus something, or 170 plus or minus something. So this is quite close to T crossover. From lattice calculations. And so what this says is that this fluid, as it's expanding, goes through this crossover, becomes a fluid of hadrons. And pretty early in the hadronic epoch, you stop having reactions which change one hadron to another. So you lose species-changing reactions. They freeze out earlier than momentum-changing reactions. So this is the analog, as I said, of nucleosynthesis. It gets us back to pretty close to the crossover, but not, well, by definition, it can't tell us about the Quark-Gluon plasma phase because we're looking at the ratios of hadrons. I should also tell you what mu you pull out. Who said, excuse me? Yes. Explain why what? Well, this is a fit parameter, and the fit that you get, it's an experimental fact that this temperature differs from that one. But it's also understood theoretically because if you look at the cross-section, so how do you change number? You have to have some reaction which is something like, well, I don't know, pi goes to pp bar. That has a very small cross-section compared to pi goes to pi. There are other ones which are not as bad as pi goes to pp bar. But reactions which change species have smaller cross-sections than elastic scattering. So elastic scattering keeps momenta in equilibrium to a later time than number ratios. Yes?
Physically, chemical freeze-out means in that
It's the time. It's the time. It's the time after which the number ratios don't change. That's what it means. And kinetic freeze out is the time after which momenta don't change, because there's no redshift here. So but from kinetic freeze out until 1 meter, 2 meters distance, where the particles make tracks in a detector, truly nothing changes. Okay. Yes.
Why needed to
Oliver.
be true that all of these different species changing interactions freeze out at the same time?
It needn't be. And there have at various times in heavy ion physics been slight glitches in this thermal model fit. And people have attributed them to that issue, but then they sort of tend to go away. Partly, it also has to do with error bars. The error bars on some of the, it's not that easy to measure omegas in heavy ion collision. Okay, the error bars on the omega ratio are quite significant. And that's actually a place where you might expect to see what you're talking about, but the error bars are big. So probably the best answer is that effect is there, but the error bars are too big to see it. Yes?
Are there any charm particles?
We'll talk about charm particles tomorrow, I hope, but they're not enough. They're not put into these fits. It would be interesting. It might be possible at the LHC. Okay. So the baryon chemical potential is strongly dependent on collision energy. We talked about this before. So if I make some sort of a log scale here, here's 100 GeV. So RHIC is at 200, and here is 10, and then below 10 comes 5. If I plot the baryon chemical potential at for collisions with a root S of 5 GeV, it's about 500 MeV. So there's a data point there. That comes from collisions at an accelerator at Brookhaven that ran in the 1980s called the AGS. At a root S of 20, which I guess on log scale is somewhere here, you're down at around between 200 and 300. So here's 200, here's 300, and there's a point here. There's a point here. That comes from experiments done at the SPS, Heavy Ion Collider at CERN that ran during the 1990s. And then the RHIC point at top RHIC energy is at about 30, which is way down here, so it's at about here. So you get for every accelerator, you get a couple of points at whatever energies the accelerator has run at. RHIC has actually run at several energies, so in fact, there's a couple of RHIC points, sort of like this. So there's some curve like this, which is just a purely empirical curve, which tells you that at low energies, you really do have higher chemical potentials. So I mentioned this in my intro to my intro. There is, in fact, data supporting the fact that for low collision energies, you get higher baryon chemical potentials than for high collision energies. And at top RHIC energies, you can just neglect mu because it's much less than the temperature. So for today and tomorrow, we're going to neglect mu completely. Not for Thursday. Okay, so here ends my context setting introduction. This is where I was hoping to get to yesterday. Question?
So can you associate length scale with your chemical freeze-out, like on your diagram?
You can associate a time scale with it. You can associate a time scale with both chemical freeze-out, and I should have looked this up. So if this is kinetic freeze-out, then there's chemical freeze-out is here, and there's a tau associated with each one. That's not a directly measurable quantity. Who asked the question? That's not a directly measurable quantity, but you can get it from hydrodynamic and cascade models. Cascade models are there's a venerable art to trying to model heavy ion collisions as the collisions of bags of billiard balls. And you watch the billiard balls rattling around, you make nice movies, some of which you may have seen. And from such calculations, which of course ignore the existence of quantum mechanics, from such calculations, you can estimate things like this. I don't remember the numbers, but certainly the kinetic freeze-out is more than 10 Fermis in time. I don't remember the number. This one is probably of order 10 Fermis, but again, I don't remember the number. Okay. So today's lecture, I want to now try and go back earlier in time and get insight not into these late time. So, it's nice that we have some sense from the data that at late times you have something which can be described as equilibrated, but really we didn't build RHIC to study an equilibrated gas of hadrons. Okay, that would be, that's it's good, but that's not what we're here for. So we want to ask about earlier time physics. And there's this ingenious observable which has a 20-year history, but I will describe it, assuming you've never heard of it before, which allows you to learn about physics at early times. And it's called elliptic flow. So, for the rest of today's lecture, there's sort of a circle of ideas that all sort of tie together. Elliptic flow, V2, which is the observable quantity itself, tau naught, the equilibration time, and eta over S. And these are all, well, what we know, these are not coupled together theoretically speaking, but what we know about them is coupled together. So what we're now going to do is select events in which the collision is not head-on. So there's a nucleus going into the board. There's a nucleus coming out of the board. They're supposed to be the same size. Although actually, people at RHIC are talking about doing copper-gold collisions, in which case they wouldn't be the same size. And so all the stuff we've been talking about, the heavy ion collision, occurs in this case only in this pink almond-shaped region. Okay, so let me make sure you've got the picture. Remember, we have two pancakes colliding. This was a pancake going into the board. This is a pancake going out of the board, and they missed. By the way, I will tell you a funny story. I will not name the theorist. A well-respected nuclear theorist, not a string theorist. I'm going to pick on one of my own. A well-respected nuclear theorist who shall remain nameless in the year 2000 said to me, RHIC is never going to work because there's no way they'll be able to aim those nuclei well enough for them to collide, which shows a breathtaking lack of understanding of how accelerators work. What you do in an accelerator is you make the accelerator physicists, not our experimental particle colleagues, but the accelerator physicists make bunches of nuclei. With this, the radii of these bunches might be millimeters or centimeters or something like that. They're not Fermis. But they have a billion or a trillion or 10 to the 15, whatever number of particles in them. Those are aimed on the millimeter scale. They go through each other. And when a bunch passes through a bunch, collisions occur. And sometimes they're head-on, but most of the time they're not. And so you don't get to aim the particles to achieve this. You have to select after the fact. You have to select events after the fact, in which, if you want events like this, you have to select them after the fact. And the way you select events like this is you select on impact parameter, which is what would be nice is if you had a knob which you could dial, which was called impact parameter. It's not quite as good as that, by selecting on multiplicity. It's a basic fact that if the collision is head-on, you get more particles in the final state. If the collision is grazing, you won't have 8,000 hadrons in the final state. So you use multiplicity as a proxy for impact parameter. 8,000 particles in the final state, collisions head-on. 5,000 particles in the final state, maybe it's this case. And so what the experimentalists do is they slice their data set into bins in multiplicity, which really what that means is they're slicing it into bins in impact parameter. So that you can then do your analysis impact parameter bin by impact parameter bin. So the experimentalists have a sample of events in which the collision was like this. And in this, yes? No. The experimentalists, the luminosities at RHIC, that's true at the LHC, where the luminosities are high. But at RHIC, the luminosities are low enough that in each bunch crossing, there's either 0 or 1 collision. What you're talking about is called pileup, and luminosities at RHIC are not so high that they have to worry about pileup. That's a good question. So there are two axes defined by this collision. There's the beam axis, which comes out of the board, and then there's the impact parameter direction. So these two axes together define what's called the reaction plane. And you can now ask about physics as a function of this azimuthal angle, which is, so remember, this scale here, the radius of these circles is 7 Fermis. The radius of the detector is 5 meters. So I did this once. If you think of drawing the detectors to scale on this scale, they're light years in size. Okay. So the detectors don't resolve position; they measure momentum. So what happens in this almond is that there's a bunch of collisions. You can think of, a few hundred proton-proton collisions happening in this almond. What you measure is the momentum of the particles coming out. So phi here is the azimuthal angle of the momentum vector of the particles that come out. So you have a few thousand, not 8,000, but a few thousand hadrons made in a few hundred pp collisions that happen to occur in this almond-shaped region. So if mean free paths are infinite, then what happens, then this is just the incoherent sum of many pp collisions, pp, pn, np, etc. And that will give us, just by the central limit theorem, that will give us a phi independent final state. Okay, this can be quantified. There's 1 over root n. It won't be precisely, you don't have infinitely many particles in the final state. You have 3,000, so it won't be precisely azimuthally symmetric. But up to finite number fluctuations, it'll be azimuthally symmetric. So this is the null hypothesis that you'd like to rule out. We're not interested in studying pp collisions so this is the hypothesis that all that happens is you do a bunch of pp collisions which happen to be located here, but then nothing interesting happens after the pp collision. The stuff you make doesn't talk to each other. There's infinite mean free paths. So that's the null hypothesis, and this phi independent final state, this is ruled out by data. Happily.
So we have neutrons.
Yes. These are nucleon-nucleon collisions, yes. You're colliding gold nuclei, so there's neutrons in there. Okay, now what's the alternative hypothesis? What's the zero mean free path limit? Well, that's hydrodynamics. Yes. That's the argument that I just made. Remember that you're seeing what you measure is momenta. And there's a pp collision here. There's a pp collision there. There's a pp collision there. There's a pp collision here. Each one makes 3 particles, 7 particles, 5 particles, 10 particles. But each one of these pp collisions, other than finite number fluctuations, doesn't know about the one its neighbors. So it doesn't know about the shape of this almond. So the momentum distribution is azimuthally symmetric. So the way to get azimuthal anisotropy is for the stuff in this almond to know about its neighbors. Yes? We'll talk about that in a second. These are all, you can measure the reaction plane, you can measure everything I'm talking about, but I'll get to that in 3 pages. When I draw data on the chalkboard. But let me give the picture first before talking about how to measure it. So here's the opposite hypothesis is that this is a hot fluid. The opposite hypothesis is that I have a hydrodynamic description. And the truly opposite hypothesis is ideal hydrodynamics. By ideal hydrodynamics, I mean eta is equal to 0. I mean mean free path is equal to 0. Remember that what Son taught you is that hydrodynamics is valid on length scales longer than a mean free path. I'm going to, well, not me, Paul Ramachki in Seattle is going to do a hydrodynamic calculation where he uses hydro all the way down to length scale 0. So he's assuming that mean free paths are 0. And furthermore, he will assume, related to that, he'll assume the shear viscosity is 0. Actually, the people who did this first in 2001 were not Paul Ramachke, it was people like Uli Heinz. So this is a ridiculous approximation. And this idealization never worked before RHIC. It's been used for 20 years as a benchmark. You think of before RHIC you thought of two benchmarks. Ideal hydro was one benchmark and infinite mean free paths was the other benchmark, and neither one of them was a good description of the data. So what is this benchmark? Well, if I have a hot fluid here, then all around the edge here it has 0 pressure. So around the edge it has 0 pressure, and right in the center here it has some maximum pressure. So there are now pressure gradients. Pressure gradients drive fluid velocities. And what you see is that the pressure gradients are bigger this way than this way. So what you get is an explosion in which you explode with greater force this way than this way. And this is familiar to hopefully nobody in this room, but to anyone who has actually worked with plastic explosives. I am not such a person. But if you want to put a shaped charge on a door, you're James Bond, you want to blow a hole in the door, you shape the charge like this way, so it blasts with greater force at the door. Okay. So this is a familiar fact from many other applications of hydrodynamics. It's the logical opposite to infinite mean free path. And as I said, it's never worked before RHIC. So the first big news from RHIC around about 2001-2 was that I'm going to draw data with a chalk in a few minutes, but talking with my hands, you got collisions that were very asymmetric. In fact, in certain parametric regimes, you could see asymmetries by a factor of 2. Twice as much momentum flow. You add up all the transverse momentum in these directions versus these directions, and it's twice as large. So this is not a small effect. So the first message before you compare to hydro is just that these asymmetries here are big. Then you want to compare to hydro, and the first comparisons that were done were to ideal hydrodynamics. And ideal hydrodynamics, for the first time, did a surprisingly good job at describing the data. And we can say more than that now, and I will. But that was the message of 2001. Ideal hydrodynamics is 0 viscosity, and it was describing the data. So now, why does this tell us something about the earliness of equilibration? If tau naught were large, the almond would circularize before a hydro description was valid. So suppose that there were mean free paths of 10 Fermis. Then hydrodynamics is only going to be valid after 10 Fermis in time. This almond is 7 Fermis in size. You wait 10 Fermis, it's not an almond anymore. It's basically a circle. So if mean free paths were 10 Fermis, you would never see azimuthal asymmetries at all. Now, so people did this quantitatively. The first people to do this quantitatively were Kolb and Heinz in 2003. And their first statement, so they were comparing early ideal hydro calculations against early data, and they said that they needed tau naught to be around 0.6 Fermi to fit the data. This was Kolb and Heinz, 2003. Right. So they started their ideal hydro at a time tau naught of 0.6 Fermi. If they started it instead at 2 Fermis, circularized it appropriately to the appropriate degree, it didn't work. Okay. And this is nowadays normally quoted. People don't normally believe the 0.6 aspect, but people normally think of this now as tau naught of around 1 Fermi. the basic logic here is that if tau naught were much bigger than 1 Fermi, so I'll put a less than wiggle. If tau naught were much bigger than 1 Fermi, you would get enough circularization that you would lose the asymmetry, the anisotropy. And this is the logic then that justifies the statement made in 2005 by Brookhaven National Laboratory that they were studying Quark-Gluon plasma. If you read the science papers that backed up the press release, what was in those science papers was the story that I've just told you. Yes.
Again, is the time in which it basically comes up.
Right. Yeah. And Tom.
Quark-Gluon plasma, because you somehow know the temperature is above the...
It comes from the Bjorkane argument. It goes, you do make the argument through energy density. The energy, from this, you say that you were in local thermal equilibrium by 1 Fermi. You use the Bjorkane argument to say that the energy density then was bigger than 5 GeV per cubic Fermi, and that comes from data. The Bjorkane argument is a very simple use of data. And then you have to use lattice QCD calculations to say that equilibrated matter at 5 GeV per cubic Fermi is a Quark-Gluon plasma. Since then, by the way, much more recently, experimentalists have detected the photons from this plasma and have used those photons to confirm that the temperatures are high enough. That's if Jamie were here, we could get Jamie to talk about that. There's issues with that still, but that's much more recent. I wasn't planning to talk about it. Question where? Yes.
You said that both the assumption of mean free path is bigger than the velocities for the asymmetry, and the effect is also occurred when not is larger. So are they related?
Yes. So all of these things are related. And so now the thing that I haven't yet put on the board is 8 over S. If you think in terms of quasi-particles, which we now know you shouldn't, but if you think in terms of quasi-particles, the quasi-particle mean free path determines tau naught. Maybe tau naught is a few times the quasi-particle mean free path. In what I just said, I just glossed over some really nice work by Dam Son several years ago, who said what I just said in a more precise way. The other thing that in a quasi-particle description, the other thing that the mean free path determines is 8 over S. So what is 8 over S? Well, 8 is the shear viscosity, S is the entropy density. And this, in a weakly coupled fluid, where you have quasi-particles with some mean free path, 8 over S is basically, it's not equal to, but it's proportional to the ratio of mean free path to spacing between particles. You can look up in the particle data book, actually not in the CRC handbook, you can look up 8 over S for air, and it's around 1,000. So air is a weakly coupled fluid, and it's a system in which the mean free paths are much longer than the spacing between air molecules, and 8 over S is very large. 8 over S for water it's temperature dependent, but it's sort of 10, maybe a little bit less than 10, certainly much bigger than 1. And water is famously a liquid. It's the liquid after which hydrodynamics is named. So to set a sense of scale, 8 over S is less than 10. You're reasonable to think about those as liquids as opposed to gases. Now, in heavy ion collisions, what does 8 over S do? Well, 8 over S, if 8 over S is too large, then this you have these shears in this initial flow, and they will just sort of they'll piss away into heat instead of giving you that nice asymmetric explosion that you were looking for. So 8 over S saps the anisotropy, just like tau naught does, but for a different reason. But well, I'm not sure. Both 8 over S, hard to separate 8 over S and tau naught because they both reduce the anisotropy. Okay. This will be one of the messages. But still, I'm going to I sort of want to start with a conclusion before showing you how you get to that conclusion. 8 over s for the Quark-Gluon plasma, which you obtain by comparing data on how asymmetric the collisions are to hydrodynamic predictions, not ideal hydro, but now viscous hydrodynamics with an 8 over s in the calculation. Exactly. And there's in a sense 3 uncertainties and 1 piece of data. So there are degeneracies. The third uncertainty you'll see in a minute. There's 3 things you want to get out, and you only have 1 measurement, so there's a problem. But as I'll try to explain, it's reasonable to say that 8 over s for the Quark-Gluon plasma is less than 0.2, which you'll notice is much less than that of water. So and for liquid helium, this 8 over s is around 1. For helium-4. So at the time that Son and his colleagues wrote their Physics Today article, they were able to say that 8 over s of the Quark-Gluon plasma was much less than that of any terrestrial liquid. Where are you, Son? There you are. Who wrote the Physics Today article? Didn't you? Okay. Anyway, you were, I'm sure, consulted. And it was true then, but I will just advertise, I'm not going to talk about the unitary Fermi gas. Son said he's going to do that late in his lectures. I'll miss that, I'm afraid. But between then and now, there's another system with 8 over s this small, and it's 20 orders of magnitude colder than the Quark-Gluon plasma. And it's these ultra-cold gases of fermionic atoms, which are studied here in Colorado in this building somewhere. They're studied at MIT. They're studied in Duke and in Texas. And they can get elliptic flow. That you have a cloud of trapped atoms, which is shaped like a cylinder. It's like, think of it like a cigar. The scale is like a centimeter this way and a millimeter that way. That's the scale. And it's held in a trap by a trapping potential. And then you turn the trap off, the thing explodes. And what you find is that this cigar, which is yay long this way and yay around this way, explodes with much greater force this way. And in fact, it circularizes. In fact, you can see, and they actually get to take pictures of their explosions, and you see in their pictures that it explodes so much that it goes from being, this is called prolate, it goes from being prolate to oblate. So they in fact can study elliptic flow also. And they can do even cooler experiments because they can take this cigar and they can torque it so that it's rotating. And now, so you have this rotating cloud. You then turn off the trapping potential, and you watch the expansion of that. And that turns out to be a great way to constrain 8 over s. And they also find that 8 over s turns out to be, so 8 over s for the cold atom, cold fermionic atoms with infinite s-wave scattering length. This is the unitary regime, which Son is going to talk about. This also turns out to be less than of order 0.2. This is data from John Thomas at Duke. So there are now 2 fluids with this. There are 2 liquids known that are this good liquids: the Quark-Gluon plasma and the unitary Fermi gas. And then there's an infinite class of other liquids known from string theory, namely the Quark-Gluon plasma and any gauge theory with a gravity dual. So this circle of ideas that emerges from analyzing elliptic flow data, if you ask why should heavy ion collisions be interesting to a broader community of scientists, not just people who are interested in the phase diagram of QCD, it's really this. It's this discovery that tells you that, first of all, it tells you that you can talk using the language of thermodynamics and hydrodynamics. It tells you that you have Quark-Gluon plasma. It tells you that 8 over s is low, so it's a very good liquid. These are the things that have attracted the attention of a larger community. So for the rest of today, I want to do 2 things. First of all, I want to give you a sense of how this quantity is actually measured, and then I'll talk a little bit about what we learned from the ADS-CFT calculations that's relevant to this part of my story. Okay, so The quantity that you measure is called V2. That's pure jargon. There's no meaning in the use of the letter V. What is it? I need space on the board. So what you measure is the number of particles binned in transverse momentum. So transverse momentum is px and py, and you can instead of px and py work in the magnitude of transverse momentum, which is pt, and phi, the azimuthal angle, which is an azimuthal angle in momentum space. And this is written, there's some dn dpt, and then you do a Fourier decomposition. Oops. Okay, so this is a Fourier this 2 here is the 2 out here is a convention, and this azimuthal angle phi is the phi relative to the reaction plane. So this is phi relative to the reaction plane. So to measure this quantity, you need to know the reaction plane, and by symmetry, you can measure, you can extract V1 and V3 from data. There's nothing stops you from extracting that from data. But by symmetry, you expect them to be 0. There's nothing in this initial condition that should give you a V1 or a V3 or any odd moment. So you expect this to vanish, this to vanish. You expect to get V2 and V4 only. It turns out that V4 effects are measured. They're measured with good statistical significance. They're somewhat interesting, but not interesting enough for me to talk about them. The one that's interesting is the first non-zero anisotropy, which is V2. Notice that because of this definition, if, as you'll see in a minute, if V2 is 0.2, that implies that the ratio of sort of up plus down to left plus right is 1 plus 2v2 over 1 minus 2v2, which is 1.4 over 0.6, which is bigger than 2. So when I tell you v2 is 0.2, that means that the collision is anisotropic by more than a factor of 2. That just comes from the definition of the observable. Okay, so how do you measure the reaction plane? Since this is, you're not going to go out and become experimental heavy ion physicists, I'll just do this quickly. The easiest way of doing it, the way that's sort of most direct from a theorist's point of view, is you divide the collision into the central rapidity region and the far forward regions. Forward this way, forward that way. In the far forward regions, you don't expect equilibration, but there's still enough interactions that you get an asymmetry. And so what you do is you measure the reaction plane at eta of plus 2 and minus 2, plus 3 and minus 3. And then you describe the particles in the central region in angle relative to the reaction plane defined at far forward directions. And this is fine so long as there is no physics that correlates a particle with eta of 3 and a particle with eta of 0. And that's the poor man's way of doing this, and in fact, that's the way that Phoenix does it. Phobos does it that way also. The other way of doing this is more sophisticated, and it's a nice piece of of physics, but I won't walk you through it. But you can also, if you think about it, how would I want to pull this out? Well, if you look at, if I decide I'm just going to look in the central region, if you want to pull this out, you're going to need more than 2 particles. Okay. Because if you just use 2 particle correlations can be faked by anything that gives you a correlation between back-to-back pairs, which doesn't know about the reaction plane. But you can define 4 and 6 particle observables, which allow you, they're called cumulants. You can define 4 and 6 particle cumulants that allow you to pull this out in a way that avoids being faked. So the experimentalists have good ways of measuring this V2, which is defined with the reaction plane in its definition. Okay, so what do they get? As you can tell, they get V2s as large as 0.2. So you can do this. You can do this slicing the data in terms of PT. So you measure the V2 for particles with different PT, and I'm going to put here 2 GeV, here 4 GeV. So you slice the data in PT and in impact parameter, and here is 0.1, here is 0.2, and you sort of get, for collisions that are close to head-on, you get something like this. And then with more of an impact parameter, you get like this. And then with a significant impact parameter, you get like this. So this is the data set with the smallest impact parameter. And this is impact parameter, which I guess is conventionally called B. So this is B of order R, loosely speaking. This is the experimental quantity is actually the proxy for B, but this for this audience, I think this will suffice. So you get V2s, which particularly at higher momenta, around 2 GeV, 1 GeV, 2 GeV, are very large. So and why do you expect this V2 effect to be larger for higher momentum particles? That has to do with the fact that when you look at higher momentum, you're preferentially selecting particles which have been boosted towards you. Okay, and if you think about where they must have come from, they must have come from a thin sheet of the almond which is on the side towards you, and that thin sheet is even more asymmetric than the almond as a whole. So the fact that as you go up in PT you get more of an effect has to do with a selection bias, in fact. Okay, but the basic message is that V2s around 0.2 means asymmetry is bigger than a factor of 2, and that's what's seen in the data for collisions which have a significant impact parameter. Now we need to compare to hydro. And now I'm in trouble because this board doesn't slide. Sabir had this problem also. Okay, so I'll have to redraw the data up here. Before I redraw the data, let me tell you, it's actually worked out very well that Son introduced hydro as he did just before my lecture. So I don't have to tell you what hydrodynamics is, but I will tell you what the inputs are to this use of hydrodynamics. So we want to now do a hydrodynamic calculation of V2. So I have to initialize some fluid in an area, transverse area in the transverse plane like that. So clearly this is going to be a 2 + 1 dimensional calculation. Most calculations to date have assumed boost invariance in the longitudinal direction. And that means that the numerical problem is 2 + 1 dimensional. There are now beginning to be some truly 3 + 1 dimensional calculations. But that's harder. So what the inputs you need, what are my inputs? What do I need to tell the computer in order for the computer to tell me V2? The first thing you need is an equation of state. And this is pressure as a function of epsilon. If you remember in Son's description of ideal hydro, what occurred in this stress energy tensor was, in T mu nu, was P and epsilon. The P and epsilon are related. For any, the microscopic physics determines some relation between P and epsilon. We will take this from lattice QCD. So this we can think of as known.
This is just take pure gluons, or you also have
Include the quarks. So, but this is in any lattice calculation there are always uncertainties, but they're small compared to the other uncertainties. So this we'll think of as known. Okay, then you need. So this is all you need. This plus initial conditions, which I guess what I should mention next is initial conditions. And initial conditions has two parts. It has the value of tau naught, and it has the profile of energy density across the almond. Pardon me? I didn't hear you. Conservation of what? Did you say conservation?
yes, on top of the equation state.
Well, that's hydrodynamics. I mean, hydrodynamics is d mu T mu nu equals 0. But this, I'm talking about the inputs to hydrodynamics. Hydrodynamics is conservation. This we'd like to know. It sure would be good if this were something that was well understood. Unfortunately, it's not. So the biggest uncertainty right now is how well. So here's my almond, drawn a little bigger. What's at time tau naught? What is epsilon as a function of x across this almond? And there are the way that this was done until about 2-3 years ago. Sort of the conventional, the standard way is it's named after Roy Glauber, as a professor at Harvard. But all it is so the density distribution of nuclei is well known. It's measured. It's been measured since the 1960s. And remember that this almond is the intersection of two circles. And what are called, if you go read papers, what are called Glauber initial conditions. And I'm not even sure that Roy deserves any credit for this. But they're called Glauber initial conditions. And what that means is that this epsilon of x is proportional to the product of the nuclear densities. So you look up in 1960s electron scattering off of nucleon data, you get what's conventionally parameterized as what's called a Wood-Saxon distribution, for those of you who've taken a nuclear physics class. Anyway, it's experimentally known what the density profile of a nucleus is. And they have an edge, they have a middle. And the idea is that the amount of energy which is dumped into quark-gluon plasma in this collision will be proportional to the number of collisions. The number of collisions will be proportional to the number of nucleons here coming this way times the number of nucleons there coming this way. And that's this. That's the Glauber model, Glauber approach. And the alternative, and so this, you can think of this as a benchmark on one side of truth. The alternative, which I really don't want to explain, but if you look it up in the literature, is called color glass condensate initial conditions. And this references a body of literature that I'm not an expert on, but the basic idea here is that when you look at a nucleus, or any hadron for that matter, when you look at it at small enough Feynman x, so when you look at the wee partons, the partons that carry a small fraction of the momentum of a proton, the gluon PDFs rise. So there's a pileup of gluons at small x that's not taken into account by Glauber. And this is an attempt to take that into consideration. And basically it says that pileup of gluons is such that what you get in this case is a epsilon of x that is more peaked at x equals 0, which means you get larger initial pressure gradients. And my own feeling about this is that these folks are correct, that this underestimates the pressure gradients, but I don't believe that they have described them quantitatively. So we who are interested in extracting tau naught have to live with the fact that there's an uncertainty in the initial profile. Okay, and then the third thing which you'd like to get out is 8 over s. So the inputs to hydro, if you're doing ideal hydro, the inputs are everything above my hand. When you do viscous hydro, in addition, you need to give the hydro, you need to tell the computer what 8 over s you're using, and this we'd also like to constrain. And you can see that there's too many unknowns here. This is not really a one-parameter unknown, but I can count. This is when I counted 3 unknowns. This was one unknown. This is one unknown, and this is one unknown. And that's why it's not possible for me to say experiments at RHIC have told me that 8 over s is such and such plus or minus such and such. You can't do that because what you need is further observables that could break this, if you like, degeneracy. But the situation, I could, well, okay. The situation right now, so there's several groups that have done current calculations. I'm going to, quote, I'm going to draw on the chalkboard plots that come out of a paper by Luzum and Romaczki. That is a representative example of what you get from these kind of calculations. So here is V2 of PT again, and I'll put the data in some color. So that you pick one particular impact parameter. So you pick one for which you get a nice big effect. So that's the data right there. And then you do a ton of different hydro calculations varying all these quantities. So let's first of all use Glauber initial conditions. And tau naught equals 1 Fermi. And then what you find is that for 8 over s of 0, you're up here. And for 8 over s of 0.08, you're right on the data. And for 8 over s of 0.16, you're well below the data. So if God told me tau naught was 1 Fermi and God told me that Glauber was right, then I could use this kind of a comparison to say that 8 over s of the Quark-Gluon plasma is 0.08 plus or minus something, which would be a reasonably small error bar. But the problem is that I don't know these. So I have to make another plot. This time I'll do CGC initial conditions. Still tau naught equal to 1 Fermi. And this time the data is supposed to be in exactly the same place. That's data again. This time, 0 is higher up. 0.08 is still well above the data. And 0.16 is right on the data. And 0.24 is way down here. So remember what I said, that CGC initial conditions means there's more anisotropy in the initial conditions, more anisotropic pressure gradients in the initial conditions, so you get bigger V2. So you get to trade off the details of your choice of initial conditions against 8 over s. If you make that initial density profile, instead of sort of looking like this, if you make it look more cuspy, I'm exaggerating, then that pushes V2 up. So then you're allowed to have a larger 8 over s to fit the data. You can play the same game with trading tau naught off against V2. And here what I will say is that the fact that I can quote from Luzum and Romaczki is that with CGC initial conditions plus eta over s equal to 0 plus tau naught equals 2 Fermi, that's the data. So in other words, if you change tau naught from 1 Fermi to 2 Fermi, this curve moves that much. And nobody thinks that 8 over s is actually 0. But the situation right now is that you cannot say that 8 over s of 0 is ruled out. Okay? You can say I think you can justify a statement that 8 over s is less than 0.2, unless you believe in some tooth fairy that makes it literally a cusp in the initial energy profile. Okay, these CGC initial conditions are pushed as hard as is considered reasonable in the peaky direction, and in that case, 0.24 is way below the data. To give you a sense, by the way, of the error bars on this data, the error bars on this data are tiny. So the issue here is not for the experimentalists to solve. It's not an issue of dear experimentalists, go measure with better error bars. It's a question for theorists to sort this out, and you'd also like more further observables. Yes?
Yeah, do we have understanding what caused the deviation in high PP result?
Yes. Oh, very good question. There's a scale here. So 3 GeV is somewhere around here on these plots. Beyond 3 GeV, hydro is not supposed to work anyway. Because beyond 3 GeV, what you're looking at when you look beyond 3 GeV is the 1 particle in a billion that came from an initial hard scattering. And it's not described by these are not yet equilibrated hard particles. So hydro is only supposed to work between sort of 0 and 2 GeV. I should have said that. So really, in a sense, you can think of it just as fitting this slope, but it actually does better than that. But in a sense, that's the crudest way of thinking about it.
All of these equations presumably give the plasma at a different temperature. Has that already been accounted in the equation of state and so on?
Yeah. Well, yes, because you're using the lattice QCD equation of state.
Okay. And so the 8 over s could also be from temperature. Right?
And in principle, it could be. That's not taken into account. Of course, eta and s both vary with temperature.
Well, the 8 over s could be a function of T over the confinement scale.
Absolutely. But and that's something which is not taken into account in these calculations. But the way I would say it is that until you can fit a presumed constant 8 over s, you don't have a chance of fitting its temperature dependence.
But you could try to rule out a temperature dependence.
You could. Someone in the room can go off and try and do that. I don't think it's been done. The real problem is this uncertainty that comes from the initial state. And there are various ways of going after this. One way is to build what is called the Electron Ion Collider and study the gluon, and by doing electron nucleus collisions to really try and study in the appropriate kinematic regime the properties of nuclei as opposed to nucleons. That's something that Brookhaven wants to do, but it's a decade away. Just a second, let me finish my thought. Another thing that is closer at hand, but not yet fully cooked enough for me to lecture on it, is the study of event-by-event fluctuations of V2. Everything I've talked about here, this data is 1 billion events averaged. But you can look at how V2 fluctuates you can look at V2 event by event, and you can have a histogram. So these are means of a histogram. And you can look at the width of that histogram. And as you might suspect in the CGC case, because of this this funny energy distribution, you get larger fluctuations. And that, I think, is the best chance. But it's difficult theoretically and it's difficult experimentally, so it's not fully cooked. Yes?
You mentioned that this problem is not experimental.
Yeah.
T0 is not is an input that comes from the experiment.
No. I mean, the experimentalists measure V2. What I meant is experimentalists measure. Sorry, I should be more precise. It is experimental in the sense that it would be nice to have other experimental observables that access the same physical quantities. That would be great. And that's why I was just saying that V2 fluctuations in V2 from event by event, studying the distribution of V2s in an ensemble of events, that is a chance. Another one, which, by the way, which people talk about, is the V2 of photons. Everything we've done so far is V2 of hadrons, but you can talk about V2 of photons. That turns out to be differently sensitive to all of this. But the thing which is not needed, there is no need for experimentalists to push the error bars down on the measurement of V2. That's what I meant to say. The limiting fact here is not the measurement of V2. Pardon me? Say that again? Are you asking, could theorists calculate tau naught? Well, so if this were a weakly coupled plasma, you look up the bottom-up thermalization paper by Son and his colleagues, and for a weakly coupled plasma, they have a nice calculation of that thermalization time. And if you push it really hard, put in rather large values of the coupling constant, you can get it to be as small as 3 to 5 Fermis. Is that fair? 5 Fermis is the number I remember from some talk you gave. So maybe you push even harder, you can get 3, but it's pretty hard to get it down to 1. So 1 Fermi indicates that the interactions it indicates mean free paths are short enough that a quasi-particle description is suspect. Same for the fact that 8 over S is so small, same conclusion. Quasi-particle description is suspect. And that's the message. Okay, so I'm actually going to go, I have two pages, but I'm going to go 10 minutes over. These experiments pose a challenge to, we're all theorists in this room. Jamie is left for Brookhaven, he's not here anymore. And they challenge us. They challenge us with a question of how can we theorists do what you were asking, which is how can we calculate, well, first of all, calculate properties of strongly coupled quark-gluon plasma liquids. Second of all, calculate things like tau naught. That's harder. And there are 3 possible responses. One is lattice QCD. Lattice QCD has no problem with strong coupling, and lattice QCD is perfect for thermodynamics. And so, we know the energy density and pressure of the strongly coupled quark-gluon plasma liquid. We've known it for a decade. But knowing the thermodynamics didn't, in fact, tell us that the fluid was strongly coupled, in fact, because, as I told you, that was a surprise. So the second alternative is perturbative QCD, and this is what many people were doing before this challenge really was put as sharply as it is now. Perturbative QCD, what I like to say is you're doing a calculation in the right theory but with the wrong approximation. So you can calculate 8 over S in perturbative QCD. And I should have said what you get, actually. 8 over S. When was I going to say that? Somehow I missed it. Oh, yeah. Right. So, sorry. In perturbative QCD, eta over S turns out to be, it goes like 1 over g to the 4th log 1 over g. And you can, of course, when you get a formula like this, there's a prefactor which is known. But anyway, when you get a formula like this, you can choose a value of g so that this is 0.08. But the g that you choose to get this to be 0.08 is so large as to make a perturbative QCD calculation ridiculous. Okay, so so to get eta over S less than 1 requires g too large, much too large, to trust perturbative QCD. Another way of seeing the same thing is that there are those people I described before who simulate heavy ion collisions as collisions of billiard balls. And so they have what are called Parton Cascade models. By the way, one thing I should have stressed is one of the really nice things about V2 is that whatever happens, V2 is generated early. Because once this almond has circularized, you don't generate any more V2. So V2 is a nice observable. It's not sensitive to details of how the hydrodynamic fluid turns into pions. That happens much later when the thing is already, all V2 has already been generated. So V2 is a nice observable. It's sensitive early time physics. So you can try and calculate V2 by doing what's called a Parton cascade. Cascade codes means you have a numerical code with billiard balls running around in your computer. The billiard balls now are quarks and gluons. And you use perturbative QCD cross-sections, calculated cross-sections for quark-quark, quark-gluon, gluon-gluon scattering. And if you put in the perturbative QCD calculations, you underpredict V2 by about 2 orders of magnitude. So, and if you want to get V2 right, you have to crank the cross-sections in your computer artificially up by factors of between 1 and 2 orders of magnitude. And then, so you're not doing perturbative QCD anymore. So, in lots of different ways, perturbative QCD can't handle 8 over S of less than 0.2. So this then is what motivates many of us from the QCD community to pay attention to what the string theory community has given us, which is the ability to calculate quark-gluon properties, quark-gluon plasma properties in other theories. So far not in QCD itself, but in other theories that do have strongly coupled gauge theory plasmas and are easily analyzable at strong coupling because of the magic of gauge gravity duality.
How large, just numerically, how large would you say G has to be large?
I don't remember. What I remember is that I wasn't, when I did this myself, I remember that
What's a typical eta with the
1. For G's on the large side of plausible, the answer is 1. Eta of S is of around 1. That's my memory from whenever I plugged in numbers into a formula with an actual constant up here.
So
They're not crazy numbers. They're a factor of 10 number. You're off by factors of 10, not a million. Okay, so to me, then what we're when people like me start using gauge gravity duality and start doing calculations in n equals 4 supersymmetric Yang-Mills theory, what we're looking for is a new kind of universality. What we're asking is, are there properties of strongly coupled gauge theory plasmas that are the same for lots of different strongly coupled gauge theory plasmas? As I like to say, I used this line on a reporter just yesterday. If you talk about quark soup, does it matter if there's peas or carrots in the soup? The viscosity of the soup, maybe it doesn't care if it was made by grinding up peas or grinding up carrots. Once you pureed the thing, who cares? So are there properties of strongly coupled quark-gluon plasmas that don't care about microscopic details, like whether there are colored scalars or not? So for me, n equals 4 supersymmetric Yang-Mills theory I like to say it's the spherical cow of strongly coupled plasmas. It's much more symmetric than QCD. It has extra symmetries, but these extra symmetries may not matter at high temperatures. The fact that it's supersymmetric is probably not that relevant to its properties at high temperatures, because at high temperatures, fermions versus whether a particle is a fermion or a boson doesn't matter. The real reason why this is so nice is that many things in it are calculable. Things that are very hard to calculate in QCD are easy to calculate so long as we take NC to infinity and the tough coupling to infinity. And we like this because we're looking for a way of calculating properties of strong coupling. So the thing that makes this whole thing appealing is that calculations can be done at strong coupling. So this is good. This is more of an issue. NC is 3 in QCD. You can argue that the corrections to everything we do are order 1 over NC squared, which is 1/9. But what happens if they're 4 pi over 9? So for the string theorists in the room, I think the big challenge here is that essentially everything that's been done has been done in the NC goes to infinity limit. It would be nice to have 1 over NC squared corrections to some of the things that I'll talk about. 1 over lambda corrections are known in many cases, but 1 over NC squared corrections, everybody tells me those are hard. Okay, so as you know, this theory is conformal. So that means you can pick lambda and it doesn't run. So we'll pick it large. And describe a strongly coupled plasma. This theory is conformal. That means when you're at some non-zero temperature, you've picked your lambda. There's no phase. There's no phase transition in this theory. The theory is different at 0 temperature than at non-zero temperature, but there's no phase transition. So you can't use this theory to study everything in QCD. Its vacuum is very different than QCD. QCD has a phase transition. This one doesn't. But maybe up at around 2 to 3 TC in QCD, the quark soup in QCD is similar in some respects to quark soup, or quark plus squark plus gluon plus gluino soup in n equals 4 super Yang-Mills theory. And there are two calculations done with gauge gravity duality that are responsible for attracting the QCD community's attention. The first is the thermodynamic calculation, which I believe Joe mentioned. In this spherical cow theory, the energy density at lambda equals infinity divided by the energy density at lambda equals 0 is 3/4. Same for the pressure. This is a calculation that was first done by Gubser, Pete, and Klebanov in about 1996, 97, 97? Just before, right. So it's an old calculation which didn't attract attention in the QCD community at the time, although it should have. It was really actually Edward Shuriak is the first person in the QCD community that I'm aware of who noticed this and started talking about it to anybody he bumped into. And what this says, you can play silly games of saying, well, I'll look at the lattice QCD calculation of the energy and pressure and try and see if it's closer to 3/4. So this is what we call the Stefan-Boltzmann. And remember, I had, when I drew my lattice QCD calculation results on the board yesterday, the energy and pressure went to somewhere in between 3/4 of the Stefan-Boltzmann value and 1 times the Stefan-Boltzmann value. And you can play games of asking whether they're closer to 1 or closer to 3/4, but I think that's not really the point. The real point is that thermodynamics is a terrible way to detect whether your fluid is strongly coupled or not. Because what this says is that thermodynamics hardly changes. The thermodynamics is very similar for the case of coupling going to 0 or coupling going to infinity. And this is the real lesson. The real lesson from the spherical cow theory is not the value, because, well, as some of you know, this 3/4, you can mess with this 3/4 a little bit also by looking at other theories. But the real lesson is that these thermodynamic quantities, we should not have been seduced by the lattice QCD results, which looked reasonably close to 1, and therefore we should not have been seduced by them into thinking that a quasi-particle description would be valid. They just don't tell you. And then the other calculational result, which combined with this attracted attention, is 8/s. And as Son will, I hope, describe soon, 8/s turns out to be 1/4 pi for these limits in any theory with a gravity dual. In any, I didn't write this right, but it's in any plasma with a dual gravity description. So this, I think, is the best candidate for a universal quantity, namely some quantity that is common across vastly many different, microscopically different Quark-Gluon plasmas. And I was deliberately asking Son to mention this fact about the spectral function. In a weakly coupled theory, as Son discussed at the end of his lecture, you expect that spectral function to look like this. You calculate it in n equals 4 super Yang-Mills theory, and it looks like this. So n equals 4 super Yang-Mills theory is a theory with no quasi-particles. Has no long-lived quasi-particles. It has sound waves but no quasi-particles. And it's a theory whose thermodynamics is similar to what you see in lattice QCD. And it's a theory whose 8/s, 1/4 pi is 0.08, whose 8/s is similar to what you see in experiment. So if this, at the end of this lecture, where we are is we have this sort of tantalizing connection between Quark-Gluon plasmas with a gravity dual and the Quark-Gluon plasma of QCD. And clearly what you would like to do is you would like to probe this connection by looking at other observables. So what I'm going to do next lecture is talk about other things you can measure. There's more to heavy ion physics than V2. So I'm going to try and talk about two different kinds of observables tomorrow, for both of which gauge gravity duality has had something to say. And we'll get to that tomorrow. Joe.